In this section, we start to get into rank of a matrix. And when I talk about rank of a matrix, I'm not talking about ranking your matrices from like, this is my favorite matrix, this is my least favorite matrix. You are matrix number 52 on the list this week. No, something entirely different. Before we start getting too deep into rank of a matrix, let's look at the spaces in which these row vectors and column vectors operate. So suppose I've got this matrix, which I'm purposely making not a square matrix. I've got matrix 2, 1, 0, 3, negative 1, 4. And I look at the dimensions of this matrix. This matrix has 2 rows and 3 columns, so it's a 2 by 3 matrix. I can look at the row vectors, right? The row vectors are 2, 1, 0, and then the other row vector is 3, negative 1, 4. So these row vectors actually operate in R3. Okay, how about the column vectors? The column vectors, there's 3 of them, 2, 3. The next column vector is 1, negative 1, and the third column vector is 0, 4. These column vectors operate in R2, right? Each of them has 2 components. So when you look at an m by n matrix, you'll notice that the row vectors operate where? They operate in Rn. And the column vectors operate in Rm. So it's the reverse of what you would think about if you think of everything in terms of row by column. The row vectors operate in the dimensions of the column and the columns by the rows, right? So when we talk about row space and column space, then that's where we start getting into those dimensions. So if you've got a matrix A that's an m by n matrix, the row space is the subspace of is actually a subspace of Rn. And that's the subspace that's spanned by the row vectors. And it works the other way if you want to talk about the column space. The column space of that same matrix A is a subspace of Rm that's spanned by the column vectors. All right, so the definitions are very similar, except one we're talking about rows, one we're talking about columns. But I wanted to put that example up there and to show you what I'm talking about in terms of the rows and columns. All right, if we have row space and column space of different matrices, it turns out they're related to each other. Remember back in chapter 2, I had said that we were talking about things that were row equivalent, and we were talking a lot about elementary matrices, and I said row equivalents would come back for a visit, and here it is. Suppose you have 2 matrices A and B, okay? 2 matrices A and B. They're both m by n matrices, and if you want to see the whole nice formal definition written out, you could take a look in the textbook, and it'll have it in there for you. All right? If those 2 matrices are row equivalent, meaning you can get from one to the other by a series of elementary matrices, then the row space of A and B are equivalent. Now, why is that interesting? That's interesting because suppose I start with some matrix A. Okay, I'm not going to write the whole matrix out, but matrix A is a 4 by 5 matrix. And I want to find information about row space and column space. It's a whole lot easier if I take matrix A and row reduce it. Because then, suppose that whatever I had for matrix A, row reduces to this matrix. I got 1, 0, 0, 0, 3. I got 0, 1, 0, 0, 0, 0, 0, 1, 0, negative 1. And then here's the last row, a couple of 1s at the end. All right, so suppose matrix A row reduces to matrix B. I want to find a basis for the row space. Well, in order to find a basis for the row space, the first thing I should do is row reduce the matrix. Now, the question is, well, if I go through this whole process of row reducing a matrix, doesn't that change the matrix? Isn't the matrix not the same as the original matrix? No, it turns out that the basis for the row space and for the column space, well, basis for the row space, I should say, is the same. So in this case, the basis for the row space is what? It's 1, 0, 0, 0, 3. I'm just reading across the non-zero rows. I'm looking at 0, 1, 0, 0, 0. I'm looking at 0, 0, 1, 0, negative 1. And I'm looking at 0, 0, 0, 1, 1. Okay. So there's 4 vectors that are in the basis for the row space. None of them are 0, so none of them are the 0 vector, and none are linear combinations of each other, or scalar multiples. So in this case, the row space, the basis for the row space has 4 vectors. At some point then, we'll begin to look at how to find the basis for the column space. And that, it turns out, is actually a theorem. If you want to find the basis for the row space, row reduce, look at the non-zero rows. So let's take a look at one that's a little bit smaller that we can do by hand. Take a look at this example. Here's my matrix. I'll call it matrix A out of lack of creativity. 1, -1, 3, 5, -4, -4, 7, -6, 2. Right? My goal is to find row space and column space. Right? Row, column space. And what I mean by this is I want to find a basis for the row space and the column space. So the first thing I'll do is row reduce, because if I go through the process of row reduction, I'll create a second matrix that is row equivalent to the first one. So whatever the row space of matrix A is, matrix B will be also, except it'll be a whole lot easier to read. So let's do a couple of linear combinations to get rid of the 5 and the 7 that's down here. So if I do -5 row 1 plus row 2, answer goes in row 2, and then let's do -7 row 1 plus row 3, answer goes in row 3. So multiply the top row by -5, and I get -5, +5, -15. So as I'm writing this, my row 1 remains the same, right? 1, -1, 3. The second row is now 0, 1, -19. And now what's the third row? If I multiply that third row by -7, I get -7, +7, -21. All right. Add the numbers together, and I get what? 7 minus 7 is 0. 7 minus 6 is 1. 2 minus 21 is -19. Oh, would you look at that? I'm going to be able to simplify this pretty quickly. So my new matrix B is 1, -1, 3, 0, 1, -19, 0, 0, 0. All right. So how many non-zero rows are there? It looks like there's only 2. This first one and this second one. I look at it. They're not scalar multiples of each other. They don't appear to be linear combinations of each other. So I'm going to claim that for my row space, the basis for the row space of A, the original matrix, are these 2 vectors. 1, -1, 3, and 0, 1, -19. Right? Anything that comes out of those 2 vectors that's a linear combination of them forms the basis for matrix A. All right, now, I want to look at the column space. In order to look at the column space, there's 2 ways you can do it. The short way is to look at the space where the columns have leading 1s. So this has a leading 1, that has a leading 1. So I'm going to look at that column and that column. So it looks to me like those first 2 columns are the places to look. But they're not the places to look in matrix B. You've got to look in matrix A. So look at the columns of B with leading 1s, and then go back to the columns in A. So these things are row equivalent, but they're not necessarily column equivalent. So we can't just read down the columns and go, oh, 1, 0, 0, -1, 1, 0, that's my column space. No, because we might have messed with things as we went from one to the other. I can go back here. The first column of the original matrix is 1, 5, 7. The second column of the matrix is -1, -4, -6. Those are the vectors that are in the column space of A. Now, there is another way to do this. The other way to do it is to take the transpose of matrix A and row reduce that transpose, and you should get the same column. So in this case, then you would read them across, right? Just like we did for the original one to find the row space. We row reduce and then read it across. Well, you would do the same thing for the column space, except this time you would take the transpose and then row reduce and read it across. All right, let's take a look then at another example. Suppose I want to find a basis for this row space. Let's look at a nice big matrix this time. Let's take matrix A to be this matrix. 1, negative 1, 1, 3, 2. Then I got 2, negative 1, 1, 5, 1. 3, negative 1, 1, 7, 0. And I've got 0, 1, negative 1, negative 1, negative 3. All right, so this matrix has 4 rows and 5 columns, 4 by 5 matrix. When I go to row reduce it, I can tell that I'm going to end up with a row of zeros because look at these 2 columns over here. You realize those 2 columns are scalar multiples of each other. So already I know that something interesting is going to happen. I'm going to save you the length, I guess, of going through and row reducing this thing by hand. I did row reduce this by hand at some point, but when we row reduce it, we come up with this matrix B over here. And the first row remains the same, 1, negative 1, 1, 3, 2. The second row is 0, 1, negative 1, negative 1, negative 3. And then I got 2 rows of zeros, which, we're not surprised at. We already saw right away that one column was a scalar multiple of the other. So there's my matrix B. Matrix A and matrix B are row equivalent because we've gotten from one to the other by a series, basically, of elementary row operations. So row equivalent implies equal row space. So the row space between the 2 matrices are the same. So if I want the basis for the row space of A, the basis for the row space of A is, look at the 2 non-zero rows. Where are they? One of them is over here, and one of them is over there. So my basis for the row space of A is the vector. I can call them vectors like this. W1 is 1, negative 1, 1, 3, 2. And the second one is 0, 1, negative 1, negative 1, negative 3. All right, so those are the 2 vectors that are in the basis for the row space of matrix A. Now, let's take a look at the vectors that are in the column space. So basis for the column space of A. Again, you could run through that process if you want, where you take A transpose, row reduce it, and then look at the rows that are non-zero. But if we look at the rows that have leading ones, right, ones in what we call the pivot spots, it's what? It's the first column and the second column. So now go back to my original matrix, look at the first column and the second column, and you come up with these 2 vectors. 1, 2, 3, 0, and negative 1, negative 1, negative 1, 1. Okay. Notice something sort of interesting between the last example and this example. In both cases, we came up with the same number of vectors in the row space as we did in the column space. Turns out that's going to be true. The row space and the column space will have the same dimension. So anytime you have an m by n matrix, then the row space will have the same number of vectors as the column space. They're in different dimensions, right? You notice that the vectors in the row space are in R5, and the vectors in the column space are in R4, but it doesn't matter. The number of vectors remains the same. So we have a name for that. We call it the rank. The rank of a matrix is the dimension of the row or column space. Now, sometimes you'll see this as row rank versus column rank. Here, I'm going to just call it the rank because the row rank and the column rank are going to be the same. So in my previous example up there, there were 2 vectors in the row space, there were 2 vectors in the column space, so I can go back to the original matrix and say the rank of matrix A is 2. All right, let's take a look at one more example, and then we'll head into null spaces. I think this is going to be another matrix where I give you the matrix, and then I tell you what it is after it's row reduced, just so we don't have to do all the row reduction on this video here. So suppose my matrix A is 2, -2, 4, -2, 2, 1, 10, 7. So this will be a 4 by 4. -4, 4, -8, 4, and 4, -1, 14, and 6. And my question is, I want to find a basis for the row and column space of A, and I want to find the rank of matrix A. All right, so the first step is row reduce. Okay, if you go through that whole process, you'll end up with a matrix that looks like this. 1, -1, 2, -1, 0, 1, 2, 3, 0, 0, 0, 1, and 0, 0, 0, 0. All right, so this has one row that's all zeros. You notice there's actually 3 non-zero rows. So in this matrix A, the basis for the row space there's 3 non-zero rows. 1, 2, and yes, even this third guy counts as a non-zero row because it's one element that's not 0. So I got 1, -1, 2, -1. That's my first vector. My second vector is 0, 1, 2, 3. And my third vector is 0, 0, 0, 1. Okay, so there's 3 vectors in the row space. Let's look at the basis for the column space. Right, and again, you can transpose row reduce and read across. I'm going to go like this and go, there's a leading 1 over here, there's a leading 1 over here, and there's a 1 in this third spot too, right? That 1 over here counts as well. If you're in doubt, and go back to the idea that we've got 3 vectors in the row space, we need 3 vectors for the column space. The other thing, if it makes you more comfortable, you can switch row 3 and row 4, right? Switching 2 rows doesn't change the vector space. It just moves the 1 from that third row down to that fourth row, and maybe now it looks a little bit more comfortable. So the basis for the column space, go back to my original matrix, is going to be 2, 2, -4, 4, is going to be -2, 1, 4, -1, and then the third column is the one that we want, the fourth column is the one we want, -2, 7, 4, 6. So you notice that there's 3 vectors in the row space, there's 3 vectors in the column space. So what is the rank of matrix A? The rank of matrix A is 3 because there's 3 vectors in each space. All right, let's keep going and talk about null space because it shouldn't take long to talk about null space. The null space is the vectors that map things onto 0. When we do this, we're going to take equations and we're going to set them equal to 0. So the null space is the solution space of AX equals 0. All right, so when you solve this, you're going to end up with a 0 vector on the other side. And then if you talk about the dimensions of the null space, number of vectors in the null space, so the dimension of the null space, we have a name for it. We call it the nullity. In this case, I think I'm actually stealing a row-reduced matrix from a previous example, but let's say that this was the matrix we started with. Suppose we started with the matrix 1, 0, -16, 0, 1, -19, and 0, 0, 0. So I got an easy read off of my row vectors, right? The dimension from my row space is 2 because the row space, the basis vectors, are 1, 0, negative 16, and 0, 1, negative 19. Therefore, the rank of the matrix is 2. All right, let's see if we can find information about the nullity. So for the nullity, I need to add a column of zeros because basically I'm saying where is x1 minus 16x3 equals 0 and x2 minus 19x3 equals 0. So now we're going to drop in a column of zeros. So 1, 0, negative 16, 0, 0, 1, negative 19, 0, and 0, 0, 0, 0. All right, would you look at that? Part of our solution is already there. I need to set up a parameter. X sub 3 is t. So x sub 2 must be 19t, and x sub 1 is 16t. So my x1, x2, x3 looks like this. I put the t on the outside, 16, 19, and 1. All right, so in the null space, there's one vector. And that one vector is 16, 19, and 1. Any linear combination of that paired up with those three variables will give me a solution of 0. What does that mean? That means that the nullity is 1. Okay, the nullity is the number of vectors in the null space. So there's one vector in the null space, so the nullity is 1. Now you notice something. Up here, we said the rank of the matrix is 2. Here we said the nullity was 1. And if you look at the number of columns in the original matrix way up at the top of your screen, there were 3 columns in the matrix. So it's not a coincidence that if I add the rank of a matrix plus the nullity of a matrix, that'll give me the number of columns. Which means if I know 1 and I know the number of columns, I can find the other. So if I know the rank of a matrix and the number of columns, I can find the nullity just by subtracting. All right? And you can work in the other direction too. So if you know the number of columns and you know the nullity, you can subtract to find the rank. This leads us to one of those equivalence theorems. So you could read the whole thing in the book, but we started in chapter 2, I think it was, with an equivalence theorem talking about whether things were invertible and did they have a unique solution. The determinant was 0. So it turns out that we can add a couple of things to our equivalence theorem. So there should be 8 items in that equivalence theorem now. If you have a matrix that's invertible and it's row reducible and it's row equivalent to the identity matrix and the determinant is not 0, then that must mean that the rank of the matrix is equal to the number of columns. And what that also means is that the n row vectors and the n column vectors of A are linearly independent. And this will come in handy as we go through future sections, but we can add that to the list. So in other words, if you have a matrix that has an inverse, then the rank of the matrix is going to be the same as the number of columns. And that means then that all the row vectors and all the column vectors are linearly independent. Another way to think about that too is if you have, and this operates by the way on square matrices we're talking about. If you know that the rank of the matrix is the same as the number of columns, then the nullity will be 0. There won't be any vectors in the null space. Go back to one of the previous statements there. If AX equals 0 has only the trivial solution, well, then it makes sense that way. All right, so that's the end of this section. Thanks for watching.